Hello everyone, I am Dr. Venkateswararao. This is my lecture 18. In the last videos, that is lecture 16 and lecture 17, we had gone through the significance of buffer solutions, what is meant by buffer solution and buffer action. In this video, we are going to calculate the pH of a buffer solutions. pH of buffer solutions. Okay, so let us calculate the pH of a buffer solutions of acidic buffer and basic buffer one by one. At first, we shall calculate the pH of acidic buffer, pH of acidic buffer. Okay. What is the example for acidic buffer? I pose a question to you all. What is the example for acidic buffer? In the last classes, we had gone through the buffer solutions, and the best example for acidic buffer is acetic acid and sodium acetate is one of the example for acidic buffer. And I already told you that acidic buffer is an example for buffer solutions of mixture. So this is a mixture, and this mixture contains acetic acid and sodium acetate. These two undergo ionization, but acetic acid is a weak acid. It undergoes feeble ionization. That means it undergoes incomplete ionization. That incomplete ionization can be represented as acetic acid CH3COOH. It undergoes partial ionization, that is incomplete ionization, because acetic acid is a weak acid, it does not undergo complete ionization. So acetic acid undergoes ionization, feeble ionization, and it forms sodium acetate ion plus H plus ions, and there exists a equilibrium between acetate and H plus ions and acetic acid. So there exists a equilibrium between reactants and products. So it is a reversible reaction, and there exists a equilibrium. So for that equilibrium reactions, we can write equilibrium constant or acid dissociation constant. Usually we call it as acid dissociation constant Ka, or that is a equilibrium constant, because it is a reversible reaction. Okay, and we can write the equilibrium constant only for reversible reactions. So acid dissociation constant or equilibrium constant is a concentration of products by concentration of reactants. So this is the equilibrium constant or acid ionization constant, and these concentrations are necessarily equilibrium concentrations. These concentrations are equilibrium concentrations. These concentrations are equilibrium concentrations. So, and in order to calculate, what is our aim? Our aim is to calculate the pH for acidic buffer. In order to calculate the pH, we should know the concentration of H plus ions, because pH is negative logarithm to the base 10 of concentration of H plus ions. If we know the concentration of H plus ions, then we able to calculate the pH, right. So, concentration of H plus ions, from this equation, from this we can get the concentration of H plus ions is equal to Ka into concentration of acetic acid at equilibrium by concentration of acetate ions CH3COO minus, CH3COO minus, and this is a equilibrium concentration. Okay, I already told you that this buffer is a mixer. In this acetic acid is there and sodium acetate is there. Of course, likewise acetic acid undergoes incomplete ionization, whereas sodium acetate undergoes complete ionization. CH3COO minus plus Na plus, it undergoes complete ionization. Okay, so whatever it is, in order to calculate the pH, we should know the concentration of H plus ions, and this is the concentration of H plus ions. This is the concentration of H plus ions. So, concentration of H plus ions at equilibrium is equal to Ka into concentration of acetic acid at equilibrium and concentration of acetate ion at equilibrium. Okay, I already told you that acetic acid undergoes incomplete ionization. For example, if you take 100 acetic acid molecules in which only 1 or 2 molecules undergo ionization. Okay, so so that's why we call it acetic acid as a weak acid. Okay, so weak acid, it undergoes incomplete ionization. So, due to incomplete or feeble ionization of acetic acid, very few number of acetate ions are formed. Very few number of acetate ions are formed from the ionization of acid, but a more number of acetate ions are formed from sodium acetate ionization. Okay, so concentration of H plus ions. So, concentration of H plus ions at equilibrium is equal to, so here the concentration of acetic acid at equilibrium, the concentration of acetic acid at equilibrium, we can take this concentration of acetic acid at equilibrium is equal to initial concentration of acid, because this acetic acid does not undergo complete ionization. For 100 molecules, only 1 molecule under 1 or 2 molecules undergo ionization. So, we can take the concentration of acetic acid at equilibrium is equal to concentration of acetic acid, initial concentration of acetic acid. So, concentration of H plus ions is equal to Ka into concentration of acetic acid CH3COOH initial, that is I shall write this here, concentration of acetic acid at equilibrium is equal to concentration of acetic acid initial concentration of acetic acid, and we can write it as a concentration of acid at initial concentration of acid. Okay, so concentration of H plus ions is equal to Ka into concentration of acetic acid initial or concentration of acid, and by concentration of acetate ions, the concentration of acetate ions at equilibrium. Actually, by the ionization of acetic acid, only very few number of acetate ions are formed, but this is a mixture. That mixture contains acetate ions from the sodium acetate. So the concentration of acetate ions is equal to concentration of initial concentration of salt. So the concentration of CH3COO minus ions at equilibrium is equal to concentration of CH3COO salt, or that is equal to concentration of salt, because it is a mixture. You should keep this point in your mind. This is a buffer is a mixture. So that mixture contains acetate ions. So we can write the concentration of acetate ions at equilibrium is equal to initial concentration of salt, that is CH3COO salt. So from this we can write Ka is equal to, this is we can write it as concentration of acid, that is expressed in normality, and this is concentration of salt expressed in normality. So here is the concentration of H plus ions at equilibrium. Okay, so applying the logarithm on both sides, log concentration of H plus ions is equal to log Ka plus log concentration of acid by minus log concentration of salt. Okay, I shall multiply the whole equation with negative sign. For the sake of my convenience, I shall multiply the whole equation with negative sign, that is negative logarithm of concentration of H plus ions is equal to negative logarithm of log Ka minus log concentration of acid plus log concentration of salt. Okay, this acid and salt should be expressed in the concentration of acid and salt should be expressed in normality, because in pH calculations we should express the acid concentration in normalities only. Whenever when we concerns with pH calculations, so we should express the concentrations in normalities, right? So negative logarithm of concentration of H plus ions, okay, we can write it as pH. So for this sake I multiply the whole equation with the negative sign. So negative logarithm of concentration of H plus ions is equal to pH, and minus log Ka, this can be written as pKa, and this is in the form of log m minus log n. So we can write it as log m by n, that is log concentration of salt minus log concentration of acid. Okay, so it is in the form of m minus n, then we can write pKa is equal to pKa plus log concentration of salt by log concentration of salt by log concentration of acid. So this is the pH of acidic buffer. This is the equation for calculating the pH of acidic buffer, and this equation is called as a Henderson equation. This equation is called Henderson equation. This equation is called as a Henderson's equation. So pH of acidic buffer is equal to pKa plus log concentration of salt by log concentration of acid. Okay. Okay, 1 minute. and log concentration of salt, this is the concentration expressed in normality. Okay, I can write the concentration of salt in normality in another form, that is we know that gram equivalents is equal to normality into volume in liters, So normality is equal to gram equivalents by volume. So we can write normality of acid or salt is equal to gram equivalents by volume, So this equation can be written as pH is equal to pKa plus log concentration of salt. Concentration of salt is gram equivalents of salt by volume by concentration of acid expressed in normality. So normality can be gram equivalents of acid by volume. And again this equation can be written as pH is equal to pKa plus log gram equivalent of salt by gram equivalent of acid into gram equivalent of salt volume by volume. So gram equivalent of salt. Okay, this is the fraction and this is the another fraction. Okay, gram equivalent of salt by volume, and this volume comes into the denominator and this volume comes into the numerator. Okay, so volume by volume. Okay, so this equation is useful in calculating the problems, in solving the problems. Okay, now we shall calculate the pH of a basic buffer, pH of a basic buffer. pH of a basic buffer. Please tell me one example for basic buffer. The best example for basic buffer is ammonium hydroxide, NH4OH is a weak base and it's a salt with a strong acid, that is ammonium chloride. I already told you that basic buffer is an example of buffer solutions of mixture, and that mixture contains ammonium hydroxide and that is a weak base, and ammonium chloride, and it is a salt of strong acid. So these two undergo ionization. NH4OH, it is a weak base, So weak base undergoes incomplete ionization or partial ionization owing to that formation NH4 plus ions plus OH minus ions. Besides that, this is a reversible reaction. For this we can write base dissociation constant or equilibrium constant. Base dissociation constant or equilibrium constant, that is concentration of NH4 plus ions at equilibrium and concentration of OH minus at equilibrium by concentration of NH4OH at equilibrium. And ammonium chloride also undergoes ionization. NH4 Cl. Ammonium chloride undergoes ionization. It is a strong electrolyte. It undergoes complete ionization, that is NH4 plus Cl minus ions. Okay, and moreover we can simply understand this owing to the complete ionization or owing to the common ion effect, the dissociation of or ionization of ammonium hydroxide is very decreased, that is ionization of weak acid further suppressed. So for calculating the pH, we need concentration of H plus ions, but we have only concentration of OH minus ions. So we shall calculate the POH and from that we shall calculate the pH, right? So concentration of OH minus ions, at equilibrium is equal to, so Kb into concentration of NH4OH at equilibrium by concentration of NH4 plus at equilibrium. So this is in the form of similarly as in the case of acidic buffer, we can write it at from concentration of OH minus ions we can calculate the POH. Okay, so applying a logarithm on both sides. Before we are applying the logarithm on both sides, concentration of NH4OH at equilibrium. So concentration of NH4OH at equilibrium, because NH4OH is a weak base, it undergoes incomplete ionization or it undergoes feeble ionization. So the concentration of ammonium hydroxide at equilibrium can be taken as concentration of ammonium hydroxide at initial concentration of ammonium hydroxide, and the concentration of NH4 plus ions at equilibrium is equal to concentration of salt at initial concentration, because NH4 plus ions, this is the mixture, you should keep that point in your mind. Okay, so going to the what is it called, common ion effect, NH4 plus ions are very high in the mixer, and those NH4 plus ions are from strong electrolyte. So that concentration of NH4 plus ions at equilibrium, we can take it as initial concentration of salt. So concentration of OH minus ions is equal to Kb into concentration of base by concentration of salt. We should express this in normalities. Okay, now we are applying the logarithm on both sides. Log concentration of OH minus ions is equal to log Kb plus log concentration of base minus log concentration of salt normality. Okay, for the sake of my convenience, I shall multiply the whole equation with the negative sign, that is negative logarithm of concentration of OH minus ions is equal to negative logarithm concentration of Kb minus log concentration of plus log concentration of salt. Okay, so negative logarithm of concentration of OH minus ions, we can write it as POH, because POH is equal to negative logarithm to the base 10 of concentration of OH minus ions. So POH is equal to it is in the form of we can write it as pKb, and it is in the form of log m minus n, that is log concentration of salt minus log concentration of base. Okay, concentration of base, and pKb is equal pKb plus it is in the form of m minus n, that is m by n, that is log concentration of salt by log concentration of base. Okay. So, this is the pOH, but our aim is to calculate the, our objective is to calculate the pH for basic buffer. We can calculate the pH from pOH, that is pH plus pOH is equal to 14. So, from this pH is equal to 14 minus pOH, 14 minus pOH. So, pH of basic buffer is equal to pH is equal to 14 minus pOH means pKb minus log concentration of salt by log concentration of base. Okay. So, this is the pH of basic buffer. This is the pH for basic buffer, and we usually call it as a Henderson's equation. This is called Henderson's equation. Henderson's equation. Okay. And again we can write this concentration of salt in normality, that is gram equivalents by volume, and this concentration of base can be written as a concentration gram equivalents of base by volume. Okay, as in the case of acidic buffer. Okay. So, these are the pH. So, pH of a acidic buffer is pH is equal to pKa plus log concentration of salt by log concentration of acid, and pH of basic buffer is 14 minus pKb minus log concentration of salt by log concentration of base. Okay. So, this is these are the equations for pH of buffer solutions. Okay. I hope you all understand this derivation, and in the next video I shall come up with change in pH of buffer solutions when we add acid or base to the acidic or basic buffer. Okay. Thank you.